distributions. And so the first thing I want you to know is that when you talk about a percentile in statistics, that percentile is talking about the percent of people below you. That's very important. You're talking about the percentage less than you. So if you are in the 95th percentile, that means 95% of the people are below you. That's why we don't talk about somebody being in the 100th percentile. The most it could be would be the 99th percentile, because 99% of the people are below you. Down below here we have a STEM plot that has 25 students. And they're in my third block AP Stats class. This must be from last year. And as you're reading this, we're going to use these scores to find the percentiles of the following student. So we look at Gannon, who's got a 72. So he's right here. If we're talking about the percentile for Gannon, how many people are below him? Just one. So he would be one person below him out of the 25 people in the STEM plot, which means he's in the 4th percentile. Not doing so hot. Mr. Bartz is very funny because he's talking about my kids and his kids, of course. So the next one is Sophia. That's his daughter. And she got a 93. So Sophia got a 93. There are 24 students below her out of the 25, which means she's in the 96th percentile. Notice how she's the highest student, but still she's only the 96th percentile because they're talking about the people below you. Okay, so what about the two students who earned a score of 80? So we've got two of them, score of 80. How many students are below them? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 students below them. So 12, whoops, out of the 25 puts them in the 48th percentile. Now, one of the things that can be kind of maddening if you're a student and you have all A's, of course, you have a 4.0. You're ranked number 1. However, if you have 1 A minus and there were 10 kids that were ranked at 4.0 and you're now the 11, you're automatically ranked number 11 out of that total because of that, or somewhere in that range depending on how certain schools do it, but that would be the next available number. And so you're ranking, even though you are the second highest person, that's how class ranks work for the most part. So it's a little bit frustrating. That's one of the reasons I think our school does not do class ranks. Pretty much.
Yes.
Okay, cumulative relative frequency. So that means totals up to that point. And it's a way to display our information graphically. It shows you the number, the percentage, or the proportion. And what you're going to find out is really this proportion, percentage. There's also another word we use later when we talk about distributions, area, that are less than or equal to that particular value. So it's kind of like a percentile. And so we're looking at what percent of calls lasted less than 30 minutes. So if we go to 30 minutes and we draw a vertical line to the graph, and then we come over to the y-axis, what we're talking about is, where do we think that is on the y-axis? And my drawing might be a little bit off, so what would you think based on where I put mine or where you put yours? 70? 70 what?
68.
68? I would say yours looks like 68, mine looks like 72. So you say about whatever you think it might be, based on where I put mine, which might not be exactly horizontal because I'm freehanding this. Mine look like 72% of the calls are below it. the reader looking at this, if you don't put a number in between 60 and 80, you're definitely going to get it wrong. Since I'm a little bit above where the 70 would be, I probably should have a number more than 70. And so this is not an exact science as far as you know the exact number, but you should be able to pick a number that makes sense based on where you drew your horizontal line. If you remember about IQR, IQR is talking about from Q1 to Q3. Q1 is at about 25%. So if I'm looking at Q1, 25% would be right about here. No? Oh, okay. So I went the wrong way. I was looking at call lengths, not that. So I should be looking at the percentages instead. So 25% maybe is somewhere right around here. And then I go down to the calls. This is my Q1. And then I would do the same thing for Q3, which then instead of being 25% would be 75%, so maybe right about here. And go down. This is my Q3. So then what I talk about is Q1, based on where I drew my lines, Q1 was equal to 12 calls, about. And my Q3 was roughly equal to 31, maybe. So if I want the IQR, when I'm doing these, my IQR is equal to Q3 minus Q1, or in other words, I'm taking my 31 and I'm subtracting off my 12, or in other words, my answer should be 19 calls. Does that sound right? Okay, so now this next thing that we're going to talk about is in my opinion, the most important thing in statistics. In statistics, what ends up happening is we're always talking about data. So sometimes you might talk about the average reaction time of a person, like you drop a ruler between the fingers and you try to capture it. Maybe it takes you 12 inches to do it, maybe it takes you 7. You might be talking about the average pulse for a human being that's 17 years old. Some people might have 57, some might have 64. And what ends up happening is all of these things are different numbers. But in statistics, you want to relay that information in a way that's common to everybody's knowledge. So what they do is they do something called standardizing. And this thing that we're going to do now standardizes anything that you talk about in statistics. It's called a z-score. And the way that you find the z-score is you take your observed value, which they call x, minus mu, which is your mean of all the data, and then you divide it by the standard deviation, and that's called your z-score. And you might have heard of the bell curve, and oftentimes students ask teachers to curve it. And what you'll learn later on is you probably really don't want that because it doesn't take into account when you have a large group of people who are much higher than the average group of people that normally would be associated with some kind of event like testing. And we'll talk about that later. So what we're going to do right now is we're going to talk about what would be a z-score for the following people that we talked about earlier. So for example, Gannon. Let's find out before we do any of this, though, what our statistics are so we can find our mean and our standard deviation. So I want you to go into your calculator, look in the stem plot, enter all the scores into list 1, and then I'm going to talk about how we use that information. After we enter all of our data into list 1, you're going to go to, this is one of the most common things you're going to do in this class, you're going to go stat, calc, enter, enter, and it's going to give you a bunch of information. So first of all, you'll notice that x bar, which we have called mu on the formula, is our mean. And then we are going to be using, and we'll talk about this later, capital SX. There are two different standard deviations. Capital SX is the standard deviation of a sample, and statistics deals with samples. And then sigma x is the standard deviation if this was a population, like in its entirety. So we will be using capital SX. You might want to make a note of that. And so for us, X bar is 80, and SX is 6.069. So I'm going to use those two numbers and go back and write those down. So I know X bar is 80, and SX, which is my standard deviation, is 6.069. If I want to standardize Gannon's score, what I would do is I would take 72, which was his score, minus the mean, which is 80, divided by the standard deviation, which was 6.069. And when I get this, I get a number that says negative 1.318. This is saying that Gannon is roughly 1.3 standard deviations below the mean. And we'll talk more about what that is later on, but that's his z-score. Sophia, on the other hand, who has a 93, we would take 93 minus 80, divided by 6.069, and that would yield a score of 2.142, which is saying that Sophia is a little bit more than 2 standard deviations above the mean. So this formula right here, super important. This is our mean, or sorry. Yep. This is our observation or our score. This is our mean. Oftentimes, the way to think about it is the X bar in the calculator. And even though they use sigma, we're going to be using SX out of our calculator because we're dealing with samples. All right, linear transformations. One of the things that we're going to talk about next is how do